And I just think the data engine side of that, so getting the data to learn all of the concepts that you're saying now is an incredible process. It's this iterative process of just, it's this hydronet of many.
Hydronet. We're changing the name to something else.
Okay. I'm sure it'll be equally as Rick and Morty like.
There's a lot of, we've re-architected the neural net, the neural nets in the cars so many times. It's crazy.
Oh, so every time there's a new major version, you'll rename it to something more ridiculous or memorable and beautiful. Sorry, not ridiculous, of course.
If you see the full like array of neural nets that are operating in the cars, it kind of boggles the mind. There's so many layers. It's crazy. But we started off with simple neural nets that were basically image recognition on a single frame from a single camera, and then trying to knit those together with C. I should say we're really primarily running C here because C++ is too much overhead, and we have our own C compiler. So to get maximum performance, we actually wrote our own C compiler and are continuing to optimize our C compiler for maximum efficiency. In fact, we've just recently done a new rev on a C compiler that'll compile directly to our autopilot hardware.
So you want to compile the whole thing down and with your own compiler?
Yeah.
Like, so efficiency here, because there's all kinds of compute. There's CPU, GPU, there's like basic types of things. And you have to somehow figure out the scheduling across all of those things. And so you're compiling the code down. Yeah. That does all, okay. So that's why there's a lot of people involved.
There's a lot of hardcore software engineering at a very sort of bare metal level, because we're trying to do a lot of compute that's constrained to our full self-driving computer. So, and we want to try to have the highest frames per second possible in a sort of very, very finite amount of compute and power. So we really put a lot of effort into the efficiency of our compute. So there's actually a lot of work done by some very talented software engineers at Tesla that at a very foundational level to improve the efficiency of compute and how we use the trip accelerators, which are basically doing matrix math, dot products, like a bazillion dot products. And it's like, what are neural nets? It's like, compute-wise, like 99% dot products. So,
and you want to achieve as many high frame rates, like a video game. You want full resolution, high frame rate,
low latency, low jitter. I think one of the things we're moving towards now is no post-processing of the image through the image signal processor. So, like for what happens for cameras is that almost all cameras is there's a lot of post-processing done in order to make pictures look pretty. Mm-hmm. And so we don't care about pictures looking pretty. We just want the data. So we're moving to just raw photon counts. So the system will, like the image that the computer sees is actually much more than what you'd see if you represented it on a camera. It's got much more data. And even in very low light conditions, you can see that there's a small photon count difference between, this spot here and that spot there, which means that, so it can see in the dark incredibly well, because it can detect these tiny differences in photon counts. That's like much better than you could possibly imagine. So, and then we also save 13 milliseconds on latency.
From removing the post-processing on the image?
Yes. Yeah. It's like, because we've got, 8 cameras and then there's roughly, 1.5 milliseconds or so, maybe 1.6 milliseconds of latency for each camera, and so going to just it basically bypassing the image processor gets us back 13 milliseconds of latency, which is important. And we track latency all the way from, photon hits the camera to, all the steps that it's got to go through to go through the various neural nets and the C code, and there's a little bit of C++ there as well. Maybe a lot, but the core stuff is the heavy duty compute is all in C. And so we track that latency all the way to an output command to the drive unit to accelerate, the brakes to slow down, the steering, turn left or right. So because you got to output a command, that's going to go to a controller, and like some of these controllers have an update frequency that's maybe 10 hertz or something like that, which is slow. That's like now you lose 100 milliseconds potentially. So then we want to update the drivers on the, like say, steering and braking control to have more like 100 hertz instead of 10 hertz, and you get a 10 milliseconds latency instead of 100 milliseconds worst case latency. And actually, jitter is more of a challenge than latency, because latency is like you can anticipate and predict, but if you've got a stack up of things going from the camera to the computer through then a series of other computers and finally to an actuator on the car, if you have a stack up of tolerances, of timing tolerances, then you can have quite a variable latency, which is called jitter. And that makes it hard to anticipate exactly how you should turn the car or accelerate, because if you've got maybe 150, 200 milliseconds of jitter, then you could be off by up to 0.2 seconds, and this could make a big difference.
So you have to interpolate somehow to deal with the effects of jitter, so that you can make like robust control decisions. You have to. So the jitter is in the sensor information, or the jitter can occur at any stage in the pipeline.
You can, if you have fixed latency, you can anticipate, and like say, okay, we know that our information is, for argument's sake, 150 milliseconds stale. Like so, for 150, for argument's sake, 150 milliseconds from photon taking camera to where you can measure a change in the acceleration of the vehicle. So then you can say, okay, well, we're going to, we know it's 150 milliseconds, so we're going to take that into account and compensate for that latency. However, if you've got then 150 milliseconds of latency plus 100 milliseconds of jitter, which could be anywhere from 0 to 100 milliseconds on top. So then your latency could be from 150 to 250 milliseconds. Now you've got 100 milliseconds that you don't know what to do with. And that's basically random. So getting rid of jitter is extremely important.
And that affects your control decisions and all those kinds of things. Okay.
The car is just going to fundamentally maneuver better with lower jitter.
Got it.
And the cars will maneuver with superhuman ability and reaction time much faster than a human. I mean, I think over time, the autopilot, full self-driving will be capable of maneuvers that, are far more than what like James Bond could do in like the best movie type of thing.
That's exactly what I was imagining in my mind as you said it.
It's like impossible maneuvers that a human couldn't do, so.